again, this may be review for some of you. You may have done this in Math 10, but I've also heard that some Math 10 teachers never got to this. I'm hoping I'm brushing cobwebs off, but I'm going to teach this as though it's brand new to you. This is right-angled trigonometry. So far, we've learned to solve for the missing sides of a triangle using the Pythagorean theorem, using good old Pythagoras. But usually this only works when we have two things. We need the hypotenuse, and you need one leg, or you need two legs. You need two sides. So hypotenuse and a leg, or one leg and one leg. Okay. For example, a builder is about to cut rafters for the roof of a house. The width of the house is 12 meters. You know what? I'm going to label that on the picture right there. And he has to make the roof 2.5 meters higher in the center than on the sides. I think I can safely say that's 2.5 meters right there. If the eaves overhang by 0.5 meters, find the total length of the rafter he has to cut. Okay, we can solve this with Pythagoras. I think the triangle that we're solving is this one here, 2.5. How long is the base? Not 12. 6. Are we good enough to go straight to our calculator? I'm going to go straight to my calculator. I've got a triangle there. So it's going to be 6 squared plus 2.5 squared square root. This might work out to a nice decimal. So I get this is 6.5 meters. Now that's not the answer to the question. The question says that there's an extra little overhang there. So I guess each rafter is going to have to be not 6.5 meters long, but how long? Okay, so each rafter will be 7.0 meters long. That's not physics. This is I've adapted this from old math question, old math lesson that I used to teach. Okay. Most of the time in physics, not always, but most of the time, you won't have two sides. Instead, you'll have one side and an angle. To do this, we need to know some basic terms in trig. This may seem obvious, Aisha, but every triangle has three sides. Well, duh, it's a triangle. Each of these three sides has a specific name if there is a right angle. The first one you already know. It's the hypotenuse. The slanty side, the longest side, always across from the 90. The second side we call the opposite. It's the one that's across or opposite from the angle that they give us. Right now, for example, William and I are sitting opposite each other. We are facing each other. The third side we call the adjacent side. The word adjacent means beside. Right now, Johnny and Will, I keep saying William, Johnny and Will are beside each other. It's the side that's touching the angle that we know or that we want to know. So, example 1 says this. Just tell me, in this triangle here, how long is the hypotenuse? Typically, what I do is I label the triangle with an H and an O and an A. What number is the H going to go next to? The 5, the 12, or the 13? 13, I put a little H there. The hypotenuse is 13. Adjacent means beside. Now the angle is right here. There are two sides beside that angle, but one of them is the hypotenuse, so it ain't that. The adjacent is what? Opposite is the one across from the angle. That's the 12. How many of you have seen this before? Some of you maybe in grade 10. I know you missed it last year. Okay, so I can go a little quicker. So sometimes when I'm teaching this for the first time, there's some student that says, oh, I get it, Mr. Dueck. The short side is always the adjacent. No, don't write this down. If this was the angle we were talking about, that would be the opposite, and that would be the adjacent. The hypotenuse doesn't change. It's always across from the 90. It's always the long slanty side. What's the hypotenuse here? 15? What's opposite to angle epsilon? That's a Greek letter, epsilon, for those of you who are wondering. We often use Greek letters as a symbol for angles. In fact, the one we'll use the most is the Greek letter theta. It's sort of shorthand in math. In math, if I see an x comma y, I assume that came from a graph. You don't need to tell me that. If I see a theta, I assume that came from a triangle. You don't need to tell me that. I can assume that. There's this shorthand variable notation that we use in mathematics. That's kind of a convention that's evolved over the centuries. So typically, we use Greek letters or capital letters for angles. Which angle is opposite? Which side, sorry, is opposite to epsilon? 12. Which side is adjacent to beta? Now, beta is that angle there. There's two sides that are adjacent. Why can't it be the 15? Because the 15 is the hypotenuse, so it's 12. Oh, on the next page, for some reason, which side is opposite to beta? Yeah. 9? Yeah. 9? Yeah. No? Nothing there? German student saying no? 9? Nothing? Okay. Yeah, 9. Now we're going to look at the three primary trig ratios. There are three right-angled triangles in the diagram below. So the small triangle we would call MAB. The larger triangle we would call NAC, sorry, the medium triangle. And the largest triangle is PAD. There's no formal order to labeling. You could have called it BAM or ABM or doesn't matter. But can you see the three triangles? There's that one. There's that one. And there's that one. Here is the key. We're not going to do this, but if I took a really, really accurate ruler and I measured that length there, opposite, and that length there, hypotenuse, I would get a decimal if I divided them on my calculator. If I took the opposite side and I divided it by the hypotenuse, I would get a decimal. If I took this opposite side and divided it by that hypotenuse, I would get exactly the same decimal if I measured with a really accurate ruler to about 1,000, well, to an infinite number of decimal places. If I took this opposite side and I divided it by that hypotenuse, I would get exactly the same decimal as the other three triangles. And the reason is, Maddie, all three of these are formed by the same angle. This is the beauty of trig. If you have a right-angled triangle, if you know the angle that's forming the rest of the triangle, all of the ratios, all of the side lengths divided by each other will give you the same answer. And it doesn't matter whether I zoom smaller, zoom bigger, those ratios won't change. It's irrespective of scale. And it turns out your calculator has all of these ratios programmed in. The ratio of opposite over hypotenuse, which we're going to abbreviate as O over H. Does anybody remember what we call opposite over hypotenuse? We give it a name. We call it the sine of an angle, S-I-N-E. Abbreviated on your calculator as S-I-N. There are two other primary trig ratios. Cosine, abbreviated cos, and tangent, abbreviated tan. The cosine ratio divides adjacent by hypotenuse. The tangent ratio divides opposite by adjacent. And to remember this, we have an acronym that I put at the top of any trig that I'm doing at the top of the page. The acronym is this phrase right here called SOHCAHTOA. That's how we pronounce it. It's an abbreviation, it's a memory trick. Although I put the trig ratios on your formula sheet, I gotta be honest, if you're having to look them up, you're having trouble. You're gonna be in trouble, okay? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And so now we have enough information to find the trig ratio of a triangle. All right. Sine of beta in this triangle here is what over what? Well, it's opposite over hypotenuse. What's the hypotenuse in this triangle here? 5, 12, or 13? What's the opposite to angle beta, the 5 or the 12? The 5. And if I wanted to decimalize that on my calculator, I could, but usually I just leave it as a fraction unless I have to decimalize it. What would the cosine of beta be? Well, cosine is adjacent over hypotenuse, so it's still going to be over 13. But what side is adjacent to beta? Sorry? I think 5 is opposite to beta. 12. Good. Tangent is opposite over adjacent. Opposite over adjacent. 5 over 12. Now, that's if we're looking at angle beta. What if we look at angle epsilon? Cosine of angle epsilon. Cosine is adjacent over hypotenuse. Well, the hypotenuse is still 13. I can do that. What's adjacent to angle epsilon? 5. You may notice that the sine of one angle in a triangle is the same as the cosine of the other angle in a triangle. The sine of epsilon is going to be opposite over hypotenuse. Hypotenuse is 13. What's the opposite side to epsilon? 12. And the tangent is going to be opposite over adjacent. I think 12 over 5. You may notice that tangent of beta, you know what? That's a typo. This should be tangent, let's cross that out, of epsilon. Let's make that more interesting. And then it will be 12 over 5. You may notice that the tangents of two angles in the same triangle are reciprocals of each other, because basically what happens is the opposite and the adjacent switch places depending on which angle you're looking at. Find the indicated ratio in fraction and decimal form to 3 decimal places. Okay. Let's just go to decimal form. So we're going to get our calculators out. Sine of beta, there's beta. Sine is opposite over hypotenuse. What divided by what? Opposite over, you tell me 8's the hypotenuse? I disagree. 15 over 17. The sine of that angle is 0.8823529412, and it goes on for a while probably, but you know what? 0.882 is what I said to 3 decimal places. As a fraction, it was, what was it? 15 over 17. Good yawn, Maddie? You awake? Cosine of epsilon. Cosine is going to be adjacent over hypotenuse. You know what? Cosine is also going to be 15 over 17. Or 0.882. Tangent of beta. Tangent is opposite over adjacent. 8 over 15 or 15 over 8? 15 over 8. Or as a decimal, 1.875. Sine of epsilon. Right there is angle. Opposite over hypotenuse. I think that's going to be 8 over 17, yes? Or as a decimal, 0.4705882353. This probably repeats eventually. Nerd math trivia. Often for prime numbers, is 17 a prime number? Is 17 prime? Yeah. Often, not always, but often, Colby, it'll be a repeating decimal, one less than the prime number. So this is probably a repeating decimal 16 digits long. 1 over 13 is often, I think it's a repeating decimal 12 digits long. Not always. That pattern doesn't always hold, but it often holds. Nerd trivia. 1 over 7 is a repeating decimal 6 digits. 0.471, if I round off properly. So far, so good, Aisha. Coming back if you've seen it before. Now, to find, turn the page. Have you all just turned the page? Yes? At the top of the page, all of us are going to write down SOHCAHTOA. You do that, and it cuts down on your thinking. There is your memory device or your mnemonic skill. To find these trig ratios, we could draw a triangle that had the appropriate angle. We could measure it, opposite, hypotenuse, and adjacent, and we could calculate the sine, the cosine, and the tangent. However, this would be both time-consuming and probably inaccurate. You need a really, really accurate ruler. Instead, it turns out these are programmed into your calculator. But you need to make sure that your calculator is set on degrees. So if you look at your calculator, unless it's a graphing calculator, the odds are pretty good somewhere on your screen you'll see an uppercase letter D really small. That means you're in degrees. If you see an uppercase letter G or an uppercase letter R, you're not in degrees. If you don't see anything, you either have a graphing calculator or your calculator doesn't display what trig mode you're in. We're going to find out. To find the sine of 30, we type on our calculator sine 30. My calculator opens a bracket up automatically, and I tend to close the bracket off. Yours may or may not do that. The bracket isn't necessary unless you're putting a bunch of stuff into the sine function. And the sine of 30, if you hit equals, should be 0.5. If it's not 0.5, now is the time to tell me, because your calculator is in the wrong mode. Everybody's get sine of 30, 0.5? What's the cosine of 15? Oh. I get 0.9659. It says to 3 decimal places, I'll go 0.966. Fill in the rest on your own, please. I'll do them up here. .428. I got 1.428 for tan 55. I got 0.035. I know tan of 45 is 1. I happen to have that one memorized. And sine of 75 is 0.966. Handy patterns. You don't have to memorize these. This is icing on the cake, but it's kind of nice to know as a built-in error check along the way. What's the sine of 10 degrees? Try it on your calculator, please. Sine of 10. What'd you get? Zero point what? 0.176? Is that right? 0.1736? What's the sine of 5 degrees? I think a smaller decimal. What's the sine of 1 degree? A smaller decimal? What's the sine of 0 degrees? Sine of 0 is 0. Okay. What's the sine of 90 degrees? 1. Sine values range between 0 and 1. If you ever somehow are doing a sine and you get an answer, or somehow your calculator is telling you that it's like 1.6, you've done something wonky. What's the cosine of 90 degrees? What's the cosine of 0 degrees? Cosine and sine are opposites of each other. Sine ranges from 0 to 1. Cosine ranges from 1 to 0. In fact, find the sine of 30. We already did it. Was it 0.5? Find the cosine of 60. Should also be 0.5. The reason I know that is because 30 and 60 add to 90 degrees. We call them complementary angles. If two angles are complements, the sine of one is the cosine of the other, and the cosine of one is the sine of the other. When we grew up without calculators, these were some of the shortcuts we picked up because you had to cut down on your calculating and your memorization quite a bit. So for example, if you find the sine of 20, can you do that? This half of the room, find the sine of 20. This half of the room, find the cosine of 70, and we'll get the same decimal. Sine of 20, what'd you all get? And that's what you guys got for the cosine of 7. I come from a large family. My mom in particular, on her side, I think there's 8 brothers. I got lots of aunts and uncles. I got more cousins than I know. And I don't know about you, but when you come from a large family, there's always the black sheep cousin that doesn't quite fit in. I have one cousin. We never know if he's going to show up at a family gathering. He's in and out of jail. If he does show up, he's showing up on his Harley with his biker friends. And we never know. Tangent is the ugly cousin of the cosine family. It doesn't follow those patterns. What's the tangent of 0 degrees? Okay. What's the tangent of 80 degrees? So tangent can be bigger than 1. Sine and cosine can't. Okay, what's the tangent of 90 degrees? What? What happened? You got an error? What's the tangent of 89 degrees? What's the tangent of 89.99? Let's sneak up on 90 and see if we can spot a pattern. What's the tangent of 89 point and then 6 nines after the decimal point? Big? Okay. What happens if you graph tangent as it gets close to 90 degrees? Right at 90, it shoots off to infinity. So tangent of 90 is undefined, or you could say, Lachlan, it's infinity, depending on whether you're doing calculus and allow for infinities or not. Not only do your calculators have all of the tangent values built in, but you can go backwards. If you give it a tangent value or a sine value or a cosine value, and this is the really useful part, it can give you the angle back. You do that by pressing the button in the top left corner of your calculator, which is either second function or shift or inverse. So, supposing you know that the sine of an angle is 0.0523, what angle did it come from? I would figure that out by going second function sine, and on most of you, a little -1 will appear next to the trig function. That's the symbol for inverse or going backwards. And if I type in the decimal value, this will give me the angle back. You get 3 degrees. Is that right? If I know that the cosine was 0.978, if I go second function cos of 0.978, I find that the angle was 12 degrees. Is that right? If tangent of angle was 0.625, what is angle? (32 degrees? If the tangent of the angle was 57.29, you know what, William? I'll bet you this is probably close to 80 or getting it like it's a bigger angle, because I remember how tangent worked, which is why I did this little calculator games with you. So second function tangent of 57.290, it's going to be bigger than 45. Oh, 89 degrees. There you go. Find the last two. (27 degrees? And this is going to be really small. 3 degrees, 2.56. I've been sloppy. I really should put a degrees next to all these numbers, because it is a unit. If you don't put a degrees there, it's assumed that you're measuring your angles in radians. I wouldn't take marks off, but I know that some math profs will next year, for example. Last thing. If I know the trig ratio on one side, I can cross multiply to get a missing side. So, for example, if I know that the sine of 45 equals opposite over hypotenuse, and the hypotenuse is 10, and x I don't know, I can solve for that. How would I get the x by itself? By what? Okay, so you're telling me a good habit, Nina, put the number in front of the trig function. On some of your calculators, if you type, so on my calculator, for example, if I type sine 45 times 10, my calculator assumes the 10 is inside the trig function, and I'll get the wrong answer. So I've developed the habit of I always put the number first, and I get the mystery side as 7.07. 1067, 7.07. B. What's the difference between A and B in terms of the x's location? What do you notice? Okay, it's on the denominator. In trig, there's going to be two main types. The x is going to be on the top or on the bottom, on the numerator or on the denominator, and thanks for using a math word. If it's on the numerator, it's really easy. Times the bottom over, times by 10. You did a bunch of the formula manipulation stuff in Physics 11. Part of one of the reasons I was doing that was to also get you good at trig. How would I get this x by itself? It's not divide by 6.5. Where is the x right now? No, it's not. It's not. Well, it is, but I don't see it that way. I see this, because that's the same equation. And my brain just sees that right away. I've done so many of these. I don't even really notice that the x is on the bottom. I know that it's the same at dividing by x on the right, same as timesing by x on the left. And why is that so much nicer? Aisha, coming back to you, how would I get the x by itself? Not multiply this time, but divide the cos over. And I get 7.58. Those are going to be the main two types of questions you get. There's three types of questions in right angle trig. The x is on the bottom, the x is on the top, or you're finding an angle using the shift button. We're going to practice all of those next class. But for now, try C on your own. I'm going to do it here. And Colby, I've done so many of these trig questions that, in fact, I don't even go through these steps. When I see that first equation, I know, oh, it's going to be 12 divided by tan 83. I swap the x and the tangent right away. I multiply the x over, and at the same time, I divide the tan 83 over. And I can do this without writing any lines down. And if you get there, I think that's great. That's my goal for all of you. 97.7? Is that right? No? Am I wrong? I didn't hit divided by. I'm totally off. I didn't hit divided by. Mr. Dueck made a mistake. That makes way more sense to me. 1.47? What's your homework? Number 1. 2, 3, 4, 5. Yeah, I'm assigning all of it. It says questions 1 to 4 will be marked in class. I'll go over the answers either later on in class today or first thing tomorrow, probably towards the end of class today. So let's do this, Mr. Dueck. I have 9:09. This class ends at 9:35. That's 25 minutes from now, yeah? So let's say 18 minutes from now, I'm going over the answers to 1 to 4.